I'm going to branch off of the P, and because the P is false, I'm going to put a not there. Okay, so as soon as I see a 0 in that row, I'm just going to put a not on that. Okay, it's the easiest way to do it. Not the most efficient, okay, but the easiest way. The Q and the R don't matter. Or they do matter, excuse me. But I don't have to make them a not. Okay, so what I'm going to do is I'm just going to conjoin these with another and. Okay. So Donnie, does that make sense as to why I'm not using an or there, sir? Okay. And then finally, I've noticed the last row with the recognizer has 0, 0, 1. Okay? There's two ways I can do this. I could branch directly off the P. Okay. Or, if I wanted to, I could put this after the not because the P is false. I'm just doing it as basic as I can. So notice the P has a 0 and the Q has a 0. Anytime we have a 0, we put a not there. Okay, so P has 0 and Q has 0, but R does not have 0. And then I'm going to conjoin these with an and. Okay. And I guess I should probably connect this. The last thing we're going to do is we're going to connect all three of those subcomponents into one big old circuit. So this, and this. And we get it. Because it's either the first one, or the fifth one, or the seventh one. Okay? There's no way they can happen at the same time. Okay? Yes, sir.
So, I mean, I know how you said you don't care whether or not we do P, Q, and R all in one big
Correct.
thing, but is that something that might matter later, varying from professor to professor?
It might, okay? So, I always try to give you guys the most efficient way of doing things, okay? You know how different teachers are. Like, you know, I mean, some of them, like, whenever I teach calculus, I don't make everyone write out every single limit law. Some of your teachers did do that, okay? So, it's just teacher to teacher, honestly. Okay, so, they might, okay? Sorry. Okay. Guys, any questions about being able to build a circuit if you're given the table? Yes, sir.
Just the process-wise, I'm trying to think through. So you do each one individually, and you ignore the other options, right? So you do it one line at a time, so then you look at, after that, you go to the next one, and you kind of forget the other one,
Yep.
so, okay.
Correct.
Because I was trying to, for some reason, I was like trying to combine to make sure it all made sense, and I was like, wait, that's probably not the right process.
And that's what we want to do. We want to try to think of things like collaboratively as opposed to independently. Okay? Yes, sir.
So when we're building these, we always want to combine them with ands and
That-
then finish with them.
Correct. And at the very end, you use the or. Okay? You never want to use an or in the middle here. Okay? Just at the very end. Because quite honestly, you need all these conditions. You need P to be false, Q to be true, and R to be true to get an output that's true. Okay? But at the end, it's either row 1 is true, or row 5 is true, or row 7. It doesn't matter which one of them is true to get a 1 as the output.
So after you draw the circuit, I know you ignored anything that had the output of a 1 when you were drawing it, but should those also work after you finish it?
Yes, sir. So if I ran, let's say I ran a 0, 0, 0 through, I should get a 0 as the output, right? So let's try it, okay?
I was trying to 0, 1, 0.
Or 0, 1, 0?
I was trying something it wasn't. I was trying 1, 0, 1.
Okay, let's try it. So 1, 0, 1, 1, 0, 1, 1, 0, 1. Okay. All right, so check this out. 1, 0, 1 through an and is a 0. As soon as you have that, okay? 1, 0, 1. This makes 0, 0, 1.
Right.
That's a 0. And then right here, 1 going through a not is a 0. 1, 1. As soon as you see 1, 0, that's a 0. 0 or 0 or 0 gives you an output of 0. Okay? So maybe you just made a copier or something like that, whatever it is.
No, I was, for whatever reason, right as you got to the end, I realized I was trying to make it become a 1.
Oh, okay, right.
That's why I'm
That's okay.
I'm 1.
And guys, if you want to, go home and try the other 4 to justify to yourself, okay? I mean, a lot of this, like, you're just taking for granted that I'm saying it works. Go home and validate it for yourself, okay? It'll literally take you guys about 4 or 5 minutes to do all of them, just to verify for yourself that it does work, okay? I mean, you could believe me or not believe me, but again, just make sure for yourself that you believe me. Okay. All right, guys. So the next thing I want to do is, if I give you guys a circuit, okay, or if I give you an expression, you should be able to construct a circuit. Okay, these are actually fairly easy problems. They're just like order of operations problems. You start inside and you just grow your circuit. Okay, so this is almost the opposite as what we did earlier. Okay, so let's go ahead and try to construct a review. By the way, it doesn't matter what order you put the circuits in. Okay, so I have P and not Q. So here's what I'm going to do. I'm going to have a P, I'm going to have a Q. Remember, nots are higher precedent than ands. So this is literally what I'm going to do. I'm going to have a P and not Q. That's it. Okay, so that's just for the first parenthesis. Then order of operations says I do what's in the second parenthesis, right? So I'm not going to worry about this or until the very end because it's outside the order of operations scope. I have a not P, so I'm going to branch off of this P that I have already. I'm going to make it a not. And then I'm going to introduce a new wire, which I'm going to call R. Okay. Those are supposed to be connected with a logic gate of OR. So now what happens is, I have both of my parentheses done. Inside the parentheses, I follow the order of operations. The last thing I notice is that I have an OR that's going to connect those. So I've done in the parentheses, now I can connect the OR. So this might be one possible circuit. Not saying it's the only one. Okay. But this is one possible circuit that would represent that Boolean expression. Okay? So, like I said, guys, think of them like order of operations problems. Start in the parentheses and just grow your circuit out based on the order of operations. Parentheses, and then nots, ands and ors, and then implies. Although we're not going to do any implies with this stuff. Okay? All right. So, guys, why don't you try the second one, just to make sure you guys get a little bit of practice doing this stuff. Start with the innermost parentheses, grow your circuit out. Okay? It doesn't matter what order the inputs go in. So you don't have to have Q second and T last. Okay, you can have Q first and T second. Doesn't matter.
T being a variable.
Correct. T is a variable, not a tautology, and I promised that I wouldn't do that again. So the moral of the story is you can totally not trust me, right? Okay. Not T is contradiction. The only reason I did that was because I've had this made up for 10 years.
Yeah, that's fine.
Sorry.
Why is that one or in the middle not like in the like it's not in the thing?
Order of operations. Okay. Order of operations, just like regular arithmetic, says you do what's in parentheses first, right?
Yeah.
So I constructed P and not Q first. After that, I constructed not P or R. And then because this is on the outside of parentheses, I did that last. So the last thing, or the rightmost operation, is the OR. Okay?
Oh, that the or. Oh, okay.
Right, this OR is the one that's on
Yeah.
the outside. Right. Okay, does that make sense, sir?
Yeah.
Okay, good. Now, I think, okay, I get it now. You were just mixing up ORs when you were doing it. Yeah, the OR on the outside, or in between those, is the one that's the rightmost OR. by the way, your circuit might look different than somebody else's, like if you're collaborating with someone, doesn't mean it's wrong. Doesn't mean it's right either, okay? But different doesn't mean wrong. At least that's what Mom told me.
Oh, you found her to be.
What's that?
Have you found that statement from a teacher?
Absolutely not.
It's cleaner, but you say like.
It got me beat up a lot. Unfortunately.
It's like all of them. It's just-
Let me give you guys another minute to try to get this together, and then we'll go through the answer, or a possible answer to that. Excuse me.
You were right the first time.
What's that?
You were right the first time.
Oh.
The answer.
Okay, the answer. Well, it's the one that I prefer to grade because it's going to be the same.
So do we have to put our letters in like that same order?
No, you can do whatever you want. The only reason I did it was because that's the order they present things.
When we're drawing the circuit,
Okay,
if
yeah, you did it.
we get the shape correctly, do we have to put the end and all in it, or is it just the shape?
Just the shape, that's fine.
I'm just, thinking about the test.
Correct, yeah. I understand that there are literally an infinite number of permutations that you guys could develop for this, okay? I'm asking you to please be kind when you're doing it, because there's 25 of you and 1 of me. So when you guys are designing these, it's a little bit of a pain in the ass for me to grade these, so try to be nice if you can. Try to make your wires straight and not like roller coaster loops or anything like that. I might just take off a point for you being a prick if you do that. I'll actually write prick point on. Alright, so one possible circuit, here's the way I'm thinking about it, okay? I'm looking at the leftmost inner parenthesis, not Q or T. So, or, is that an okay. So, and then I noticed that the next possible would be not P or R. So I have a not P or R. Now, inside of the parentheses, I notice that there's an and between those two parentheses. So what I'm going to do is I'm just going to connect those with an and to make it nice and easy. Okay, not saying that this is the way you have to do it. This just might be the easiest way. So what that does right there, that takes care of the leftmost inner parentheses. Okay. Last thing I have to do, I just have to make a circuit for P or not T. So I have a P, and I have a T. So here's my T. It's going to get connected with a not. Then I have a P. It says or, so it's going to be P or not T. And then the last thing I notice is that completely outside of any parentheses is this or. So by order of operations, I would just connect these with an or. Okay? And like I said, this is one of an infinite number of possible circuits that you could construct. Okay? I'm going to guess several of you guys had, go ahead, sir.
It's nice to see your ors don't look any better than mine.
Oh no, mine are horrific, okay? Yeah, and I apologize, I've been doing this for years and it's actually looking worse than when I started, so, sorry about that. So I guess by the time I'm like ready to retire, they're just, all my gates are gonna look exactly the same, so, sorry about that. Okay, guys, any questions I can answer about constructing a logic circuit given the Boolean statement? Okay, not too difficult. Okay, last thing I wanna look at, with Boolean circuits is, if I give you 2 circuits, how do I know that they're the same or how do I know they're different? Okay? There's actually 2 ways that you can do this. Okay? So, Boolean circuits are equivalent. And maybe you guys can help me out and answer this. Okay? What's one way that I can tell that 2 Boolean circuits are logically equivalent to one another? Donnie? So basically, input-output table is the same, right? I mean, if they do the same thing, they're logically equivalent. They are not equivalent, they are logically equivalent. Okay, so let me put the word in here that they are logically. Oh, shoot. Thanks, technology. Oh, that's even better. Never mind, thanks, technology. So they are logically equivalent. So one way to do this is to do the in-out tables. Okay, I like that. Does anyone else have another way that we might be able to decipher this?
Simplify
can make a Boolean statement and simplify them both, right? It's a little bit more painful, but it might be quicker depending upon what we're looking for. Okay, so they have the same simplified Boolean statement. Okay. So two different ways that you guys can determine if two circuits are logically equivalent to one another. Okay? You can make an input-output table, or you could just design the Boolean circuit and you can see that they work out the same. Okay? The first of these two is extremely easy to do that with. Okay? So let's do that, guys. Let's just make an input-output table, and then I can make a Boolean circuit and for both of those, and I'll show you that they both work out the same. Okay? So from the input-output table, so we have 1, 1, 0, 0, 1, 0, 1, 0. And I'm going to call this one circuit 1 and circuit 2. Let's just call this one C1. Let's call that guy C2. Okay. All right. I bet you everyone in here can probably figure out the input-output table just by virtual inspection. Okay. In fact, when I was taking linear algebra, my teacher said one of the most dangerous things you can put is by inspection as a justification for a step, because then you can just put everything by inspection, even if you have no idea what you're doing with it. So I don't accept by inspection as a justification. All right, but regardless. All right, let's say I throw 1, 1 through this gate. I get a 0. And as soon as I get a 0, guys, through either of them, what do I know about the complete output?
0.
It's 0, right? So it looks like that 1, 1 for circuit 1 gives me a 0. What happens, guys, with 1, 0? It's a 0 as well, right? Because think about it. If I throw a 1 through the NOT gate, it becomes a 0. And anytime you have a 0 with an AND, you're done. Okay? Does the same thing happen with 0, 1?
Yep.
Yep. So we're hoping that if 0, 0 doesn't work, then we just got basically have a